So hopefully you've been able to have a go at the worksheet that is on the EngBAM website. If you haven't had a chance to have a go yet, I'd recommend that you don't watch this video and you have a go first, and then if you get stuck, you're more than welcome to come and have a watch of this video to see if you can get any helpful tips, tricks or pointers to be able to get you through the worksheet. So basically what we're looking to do here is just to go over stage by stage roughly the tasks that we've been set on that worksheet. So the first thing that we are looking to cover is about the Reynolds number. So the Reynolds number equation is Reynolds number, and then on the numerator we've got rho, which is the density, times the fluid velocity, times the pipe's inner diameter, all over the viscosity, or mu, which is the Reynolds number equation. So the Reynolds number is a dimensionless number. This means that it doesn't have any units because it is a dimensionless group. Don't worry about too much about what that means right now, but the Reynolds number is something we use to classify the flow of a fluid through a pipe, or indeed any flow of fluid. So if you have a low Reynolds number, chances are you'll be in the laminar flow region, and if you have a really high Reynolds number, you're in what we call the turbulent flow region. This becomes important when you're trying to pump a fluid in industry or to judge the amount of mixing you're going to get and the reaction conditions that you're going to need to operate in. So the Reynolds number is something that comes up quite often when you get into designing and doing chemical calculations within chemical engineering. So this is just something that we're going to use now. You'll also see on that worksheet, you'll have an equation called Q equals UA. So this is the volumetric flow rate is equal to the velocity times the area. So if we look at the unit to minutes, the volumetric flow rate, the units of that is meters cubed per second, and then our velocity is meters per second, so it makes sense that we're timesing by a meter squared to get our volumetric flow rate. So first thing we want to do, as we saw in our earlier videos, as we have to scroll down quite a bit, it would be helpful to be able to freeze our top panes. So what we're going to do is go over to A8 as the cell just to freeze those top 7 rows. Then we're going to go to View, Freeze Panes, then Freeze Panes again. So you can see if I now scroll down, that's all frozen. So that is the answer to your first bit of the worksheet. And the next step that we want to do is we want to be able to calculate the area. So this is the cross-sectional area of the pipe. So we will need our equation for area of a circle, which is pi r squared. And remember, we've got the diameter here. So we want to go into the cell, start with our equals, to enter pi. In Excel, you want to do pi and then open and shut brackets, and multiplied by half the diameter squared. So this is our pi r squared, and this gives us an area of 0.00314 meters squared. So this is your next bit done. And then as we have the area, as you can see we need here, to be able to get the velocity, it's going to be our volumetric flow rate divided by our area. So that's just this equation rearranged. So if we come over here, we need to look at doing our absolute cell referencing. So we want to divide our volumetric flow rate by our cross-sectional area, and that gives us a velocity of roughly 0.15 meters per second. And then remembering to do our absolute cell referencing, this only needs to be for the area, as we want to keep referencing back to the area while we're changing the volumetric flow rate. So again, bottom right hand corner of this cell, you should see the black cross appear. Click that and drag it down, and we have calculated the velocities. So that is the next stage done for you. And then our final calculation stage is simply just calculating the Reynolds number. So it's a bit more of a complicated formula. So again, we go our density multiplied by our velocity multiplied by our diameter all over our kinematic viscosity. So here again, the only thing that's changing is the velocity. Everything else we would like to have some absolute cell referencing, like so. And then again, bottom right hand corner, drag that one down and we have calculated our Reynolds numbers. So that is all of our calculations done. I'll just delete this. Our final section that we want to do is we want to create a chart. So come insert charts, select our scatter graph, bring that over here. We can right click on our graph, select data, and we want to add. So our series name is Reynolds number, we can call it Reynolds versus velocity. We put there, doesn't really matter. Then select our X series values. So our independent variables are velocity in this case, so that's going to go on the X-axis. And then our Y-axis, so our dependent variable is going to be our Reynolds number. Again, click on that there, drag down to select, click OK, OK again. You can see here, if I zoom out, I've got a graph that looks very similar to one of the example videos. And so again, you can add some axis titles to make it look a little bit nicer. If you wanted to change the color, you're also welcome to do it, or you can change what the points look like. So that's our Reynolds number there. We don't need to worry about any units as it is a dimensionless group. Then along the bottom, we can add our velocity, which is meters per second. So that's that there. And then what sort of trend line do you think we're going to need for this? Well, as you can see, we've got a linear relationship going on between the Reynolds number and the velocity. Again, if we look at the equation doing, it's Reynolds density times the velocity times the pipe diameter all over the viscosity. The rho, d, and the mu are all constant, so that could be rearranged to be Ku, where K is our constants. So therefore, this is a linear relationship, which you should be able to recognize, and the K will in fact be the gradient of our line. So we can go here, can go to more options, and then think which one's going to be most appropriate. In this case, it is a linear one, and then if we scroll down here, we can actually add our equation to the chart. So that's 2000x. So our rho times d all over mu is actually equal to, I beg your pardon, that is 20,000x. So the 20,000 is our value of k. So this is how we could actually work out unknowns if we had a graph. But that is your final plot. As an extension, the worksheet suggested being able to average out these experimental numbers on the side. These ones have been sorted, so it's from lowest to highest along here. But if you hadn't done that, you could average out each one of the runs. So for example, you've got 2, 3, 1, find an average value of that, and then plot the average Reynolds number and velocities. And this will mean instead of getting a group along here, you'll get one singular point. And from there, you could calculate some error bars, etc. And you'd end up with a tidier looking chart. So I hope you found that useful, and I hope you've been able to have a good go at the worksheet. And you now feel a little bit more comfortable using Excel as a tool for your science courses or for engineering in the future.